And this is joint work with Yoshiro Okamoto and Ryuhei Uehara and Takeaki Uno. First of all, I should confess that this talk is not quite new. I mean, this work was presented also at TMC 2011. But it will be nice to give this talk here, but because we have a lot of interesting open problems. So let me start. What are the definitions? In this work, we studied graph parameter spanning tree congestion. This graph parameter is defined only for connected graphs, and let T be a spanning tree and of a graph G, connected graph G, then the detour of an edge UV in the original graph is a unique UV pulse in T. For example, here maybe AF, yes. Here AF, the detour of this edge in this spanning tree is this path of length 2, okay? And for this edge, we have this green detour also here and here. Detour for this edge AB, for example, is AB itself, okay? And the congestion of an edge E in the spanning tree is the number of edges in the original graph whose detours contain E, okay? So the condition here is 2 and 3, 3, 3, 2. For example, this edge is used by the detours of B itself and for FE and BC. So in other words, the condition of an edge in a spanning tree is the size of the fundamental cut defined by this edge. Okay? And the condition of an spanning tree is the maximum condition over all its edges. So this tree has condition 3. And the spanning tree condition of G denoted by STC is the minimum condition over all its spanning trees. This is the definition. It's clear? Okay. So this is a spanning tree condition, and let's try. Okay, let me give you some examples. So this one is trivial. The graph has spanning tree 1 if and only if it is a tree. This is trivial. Okay? And this is not so trivial but easy to prove. The graph has spanning tree condition at most 2 if and only if it is a cactus like this. And this one is more interesting. If the graph has spanning tree condition at most 3, then it should be planar. And also note that this parameter is not closed under any of minor operations. Okay. So this is the standard form of the decision problem. We are given a connected graph G and a positive integer k, and the question is the graph has the spanning tree condition at most k or not. Okay. And this is the parameterized version, parameterized by the solution value. And in this talk, I will speak about mostly on this decision problem, some for this parameterized version. Okay, let me give you some known results. Yes, in the positive side, the spanning tree, the decision version is linear time solvable for ultra-planar graphs. Indeed, you can find the optimum value in linear time. Maybe, I'm not quite sure, but by standard DP technique, you can find some XP time algorithm for bounded treeless graphs. And also, the parameterized version is linear time solvable for these cases. If k is small enough, or the graph has bounded maximum degree, or the graphs are apex minus 3. And on the negative side, the decision version is be complete for even for planar graphs, and the parameterized version is also NP complete if K is at least 8 and the graph is K6 minor free and has only one vertex of unbounded degrees. So these results are sharp in some sense. But these results are restricted to some sparse graphs. These graphs are sparse because they are planar or minor free or something. So the motivation of this work is to study the complexity of this problem for non-sparse graphs or dense graphs. Okay, there are two important graph classes that are dense in some sense: Chordal graphs and Chordal bipartite graphs. I think I can skip the definition, but let me show you some examples. This graph is not Chordal because it has 4 cycles, as in this subgraph. But if you put this edge, then graph becomes Chordal. And this is not Chordal bipartite because it has an induced cycle length 6. But if you put this edge, then graph becomes Chordal bipartite. Okay, and yes, they are dense in some sense. For example, Chordal graphs can contain any arbitrary large Greeks, and Chordal bipartite graphs can contain arbitrary large bipartite Greeks. So they are our target, and it is known that for complete graphs and complete bipartite graphs, the spanning tree condition problem is easy. Yeah. Also, the fixed parameter version is linear time solvable for Chordal graphs, because it is known that a Chordal graph has large tree widths if and only if it has large creek, and it is easy to show that large creek implies large spanning tree congestion, and the parameterized version is linear time solvable for bounded tree width graphs. So we can first check the tree widths. If the graph has large trees, we can throw it away, and after that we have bounded tree width graphs. Okay, so the parameterized version is easy for Chordal graphs. I could not come up with similar idea for Chordal bipartite graphs, but you can maybe obtain some similar argument for Chordal bipartite graphs. So from now on, I'll concentrate on this version, just the standard decision version. The result is negative. It is NP hard for both classes, or they have more simple subclasses, and the problem is NP complete even for these simple graph classes, split graphs and chain graphs. So let me define these graph classes. Maybe you don't need the definition of split graphs. This is not split, but if you put this edge, then graph becomes split because these 4 vertices form a creek, and these 2 vertices form an independent set. Okay, I think I should define chain graphs. Okay, a bipartite graph is a chain graph if it has no independent H pair or the 2K2. For example, here you have independent H pair, AF and CD, because they don't share their endpoints and there is no edge between the 2 vertices and 2 vertices. But if you put this edge, then there is no independent H pair, and this graph is a chain graph. Okay, and we prove that the decision version is NP complete even for these graphs, these graph classes. Okay. And so, because the problem turns out very difficult, we also give an exact exponential time algorithm. So let me summarize our result. We show that the problem is NP complete for split graphs and chain graphs, and That's for chordal graphs and for chordal bipartite graphs. And we also show that for any connected graph G with m vertices, its spanning tree condition can be determined in order 2 to the n time. Okay. So I'd like to emphasize that our hardness result for chain graphs is somewhat surprising. Maybe you can say no, but okay, let me give you some reason. So many problems are point time solved for superclasses like bipartite prolongation or biconvex or convex or interval bigraphs. And also, any chain graph has critic widths at most 3, namely their distance heredity, because they don't have any independent edge pair. And also, to the best of my knowledge, no graph parameter problem is known to be NP-hard for unweighted chain graphs or uncurved chain graphs, unlayered chain graphs. I'm not sure this is only to the best of my knowledge, so I'm eager to know concrete examples. If you know some problem is NP-hard for chain graphs, please let me know. Okay. Yes, let me give you some ideas about proof, NP-hardness. First of all, if we can use weighted edges in the graph, then the reduction would be very easy. But we want to show the hardness for unweighted graphs. But we can simulate, in some sense, we can simulate the weighted edge by parallel paths like this. If you want to have a weighted edge here with integer weight W, then you can simulate this by adding W parallel paths of arbitrary lengths between them. So you can have weighted edge, and if you have weighted edges, then you can force some edges. Here is the lemma. If let's assume spanning tree T of a graph G has condition 3 at most K, then and also if all edges incident to X in G has weight more than the half of K, then all those edges should be in T like this. In graph, these edges have large weight, then it should be in the spanning tree, because if we don't have this edge, for example, then we have this kind of detour for this edge in the spanning tree. Then this red edge has large congestion, because this edge separates these two vertices and this vertex, and so the congestion of this edge is at least the sum of these two edges. It's larger than K. Okay. So you can force some edges. And if you force these edges, you can embed an assignment problem, an instance of assignment problem in the spanning tree. Here's the lemma. If all edges incident to X are forced in T, and there is a vertex here, which neighborhood in the graph is contained in the neighborhood of X, then this should be a leaf in tree if these edges are forced. Like this, it should be a leaf. This corresponds to an assignment like this. So you can embed an assignment problem like 3 partition. So using these ideas, you can easily embed an instance of 3 partitions to the graph, and you can easily modify the graph to be split graphs or chordal bipartite graphs. So this is the first part, but unfortunately we cannot use that weighted edge gadget for chain graphs. because introducing some weighted edges, we also introduce some independent edges in the underlying unweighted graph. So you cannot use weighted edge for chain graphs. So we need some new idea, and we embed somehow two copies of an instance to the graph, and we can force some edges in one of the copies of the instance, so you win. Okay. I skipped this detail, but this is the main idea of reduction. So I will also talk about something about our exact algorithm. A naive approach is to examine all spanning trees. Yes, it is very naive, but it runs in order 2 to the n. Here, fair m is the number of edges, but it's too slow. So indeed, we can do better. Instead of all spanning trees, we examine all possible combinations of vertex subsets. And the number of pairs of decision vertex subset is 3 to the nth. Then a dynamic programming approach gives n over 3 to the n time algorithm. And we can do more better. We use the first subset convolution method, and we got over 2 to the n time algorithm. I didn't talk about anything in detail, but it is not so complicated if you read the proof. Okay. So they are our result. I think this is most important part of this talk. Open programs. We have a lot of open programs, okay, on the spanning condition. So I think this is most important problem here. Spanning tree condition for co-graphs or Quick-Quiz at most 2, because the problem is NP hard for Quick-Quiz at most 3. So how about for co-graphs? How do you think? We found that three approximation for co-graphs is very easy. Okay? If a co-graph is also Chordal, then you can find trivially the optimal solution in linear time. But we don't know the exact complexity of this problem. I think it would be in P, in my opinion, but I'm not quite sure. Next one, for interval graphs, we don't know the complexity. Even for proper interval graphs or co-chain graphs, we don't know. Also, the problem can be solved in XP time, I think, for about 2 years graphs, but it is not known the problem can be solved in FPD time when parameters by 3 wheels. Okay, and approximation. We don't have any approximation algorithm, but there is a constant lower bound for the approximation ratio, so there is no P just unless P equals NP. And for case, the complexity for KSDC is open for these values. Okay, this is the end of my talk. Thank you.